Hello my friends, here's a very nice question about sending objects from the moon to the earth. So theory has it that we can ideally send objects from the earth, moon to the earth using magnetic field and magnetic force, and we can continue sustainable life on earth in the future using this idea here. How it goes is that we put the material, we apply a current. There's a current, and we apply a magnetic field, background magnetic field to the current, and the magnetic field will push the objects, and we will reach them to desirable speed, and we'll let them go at that speed, and they will shoot. Ideally, they would come to the earth, close the earth orbit, where somebody can pick them up and carry them to the earth. So this question is about that idea. A device called a railgun uses magnetic force and currents to launch projectiles at very high speeds. An idealized model of a railgun is illustrated in figure below. A 1.2 volt supply is connected, so this is our delta V. It's connected to two conducting rails. One rail will be that, of course, this is a conducting rail. And here you go, the other side. A segment of copper wire in a region of uniform magnetic field. So this is our copper wire. And we have magnetic field into the board here, into the screen. Slides freely on the rail. Logically, we would of course know that the wire will slide in this direction, but let's go ahead and apply right hand rule for practice here. We don't want to slide it in the other direction, but the current will be in this fashion here, plus to minus. So in the system, current goes clockwise, and on the wire, the copper wire, the current is down. Applying my right hand rule, I'll put my arm and fingers down first, and I'll roll my fingers towards the magnetic field, which should be into the board. Once I do that with my right hand and open my thumb, it will show me the direction of the force, and it will be to the right. So this is my force here. So this is direction. The wire has 0.85 milliohms of resistance. So we already studied that each wire that we use in a system will have a resistance. So this guy seems to be having a resistance that is equal to 0.85 milliohms. I'm going to convert this to ohms. 0.85 times 10 to minus 3 ohms. And a mass of 5 grams, or the mass of the wire is 5 grams, and that's 5 times 10 to minus 3 kilograms. Ignore the resistance of the rails. There will be some resistance to the wire here. We are ignoring that. And of course, this system will be built in a way that the resistance is minimum. So ignoring that will be a good approximation. When the power supply is switched on, here is our questions. What is the current in the system? And for that, we have this simple circuit, assuming the wire behaves like a resistance. It's just one resistance circuit. I'm gonna redraw this resistance over here. So we are assuming we have, since the wire has an inner resistance, We're assuming we have a resistor here connecting our circuit. There's a current flowing, and that current can be found using delta V over R. And our delta V is 1.2 volts. So I in the system is equal to delta V over R, Ohm's law, 1.2 volts divided by 0.85 times 10 to minus 3 ohms. Having very low resistance will give us a very large current. I'm gonna rewrite this here. And the current will be about 1411.8 amperes. So large current will give us a large force, magnetic force applied to the wire. What are the magnitude and direction of force on the wire? We already guessed the force, direction of the force. This is the magnetic force here. And we'll find its magnitude. It's the current times the length of the wire inside the magnetic field times the magnetic field times the sine alpha. Alpha being the angle between the magnetic field and the current, which is 90 degrees in this case, and sine alpha is 1. So we can drop sine alpha. And F magnetic will be 1411.8 amperes times the length of the wire inside the magnetic field is given here, 15 centimeters. That's equals to 0.15 meters. So we put that in. Times the magnetic field was given as, trying to find the magnetic field. Are we given a magnetic field? Should be. Okay, here we go, 0.8 Tesla. The question didn't mention it, but it's given down here, 0.8 Tesla. Once we do all the calculations, we're going to find the force to be 169.14 Newton. Now comes another beautiful part of this question, connecting our knowledge from this part of the course to the first term. What will be the wire's speed after it has slid a distance of 1 meter? So it slids a distance delta x of 1 meter. What will its speed be? When I talk about speed, I remember kinetic energy, being related to speed. So I want to use kinetic energy of the wire to find the speed. And how do I find kinetic energy? Using work is equal to change in kinetic energy. K final minus K initial. Initially wire is at rest, so initial energy is 0. This will give me the final speed. How can I find that work done? Is force times the distance traveled along the force. Remember? So my force is 169.14 Newton. Distance traveled is 1 meter. The work done will be equal to, from here, of course, it's just times 169.14 joules. And inputting that over here, my final kinetic energy will be equal to that. Let me go to a color, different color here. So I'm going to input this guy over here. I'll say K final is equal to 169.14 joules, and k final is 1/2 m. V final squared, v initial is 0, so we call this v, and that's equal to 169.14 joules. As we solve for velocity, we will divide each side by 1/2 m and take square root. So after we do that, we'll find the speed of, go ahead and do that yourself, 8.23 meters per second. Alright, see you in the next video.